Hi there, everybody, and welcome. It's Professor Thayer, and today we are going to continue our discussion of quantum mechanics and physical chemistry for the life sciences. Today, we are going to take a look at how to solve the classic wave equation. But before we do that, we're going to need to learn how to do separation of variables because the classic wave equation has two variables. It has position and it has time. So what we're going to do is we're going to learn how we can take that original equation in two variables and separate it into two separate but related equations that will each be second-order linear homogeneous differential equations. And then we can go ahead and use that procedure, which we learned last time, in order to solve these equations. So I'm just going to put my timer on so I keep track of how long I have been talking. So what we're going to have in store for us today then is taking a look at how to do the separation of the variables, which I have done in a worksheet handout for you. If you're in my class, you can pick that worksheet up off of our Moodle page. I also have it reproduced in what I'll be sharing with you on the screen today. And after we have solved that, then what we're going to need to do is we're going to need to actually go through that procedure of solving the second order linear homogeneous differential equations to see what the answer is. The reason why we are looking at this solution is because it is very similar to what we're going to need to actually solve in the quantum mechanical world. We are working our way up one step at a time from how to do the math, which is what well, first of all, what we motivated quantum mechanics in dawn of quantum mechanics. Last time we looked at how to do the math to solve these kinds of differential equations that we need to solve. Today we are going to actually use that to solve our first actual model problem. It's not just a math problem, but it actually has a meaning. Next time we're going to take a look at the Schrödinger equation, which is going to define what we need to solve, and then we will be doing the particle in a box. And from there, we can extrapolate to other kinds of models and take a look at what the applications would be in the rest of the quantum mechanics world, which quickly gets mathematically very difficult to solve, but you can see exactly where that's going, and then you are in great position to go and solve those at some point if you so desire. We will not be solving those in this class in particular, but you will see what the solutions are, and you will have the tools to go and solve them if you wish. And I can certainly point you to places where you can read up on that. All right, well, there is no time like the present to get started, so I'm going to go ahead and turn off my camera and turn on the share screen because looking at the ceiling is just not going to be that exciting. So here's that, because I am going to be writing on this. Okay, so now you should see my screen. If I can just get this out of the way. Put this one down. Put this one up. All right, and here we have the separation of variables information over here, and I guess that's as wide as it gets. All right, great. I'm just gonna put this down. And okay, so then we mentioned that we would be using the separation of variables in order to solve these equations. So let's go ahead and just zoom in and take a look at this this little worksheet. And I'm just gonna put on my pen here so that I can be making some comments as we go. Let's just make sure. Yep, pen is working. Good. Okay, so just to make sure we're all on the same page, when we're talking about ordinary differential equations, these are the kind of equations that you saw in your introductory calculus class. And so you had derivatives in them where, okay, so this is, for example, the second derivative. And let's see, actually, I think I'll just put the pointer on, right? So this is the second derivative right here. There's no first derivative, right? So this is an example of an ordinary differential equation, otherwise known as the ODE, which has a single independent variable. In this case, we're taking the derivative with respect to x, right? Because we have d squared dx squared. And that is what that means. The partial differential equation is what we are going to be seeing today. Let's mention that when we were solving for the second order linear homogeneous differential equation, sorry, it's pointer is not doing what I wanted it to do. When we were solving that, when we were in fact taking a look at ODEs. So that's part of the reason why we need to understand about some of these other kinds of things, because we cannot use the formulation that we learned last time to solve the partial differential equations. So we're going to have to try to break the partial differential equations into some smaller pieces. So here is our partial differential equation that we're going to be looking at, and the way that we recognize it, okay, first of all, is that it has this funky D instead of a regular D. This is the Cyrillic alphabet kind of a D. Looks like the delta, lowercase delta. And the reason why we switched to that is because the function is with regard to two different variables. You see that this one is an X and a Y. That's exactly the kind of a situation we're going to have today. And then we have, okay, here's another one over here, right? This one also is a function in two variables, and it's a second order because we have this higher level term. There also could be dx terms, right? A first order term, but this one simply just doesn't have that. But the point is this one has only one variable and this one has two variables, and the two variables is what is going to cause us the problem that we need to deal with first. And that's why we need to do the separation of variables. So the separation of variables procedure is when you attempt to take a partial differential equation and separate it into two independent equations that you can work with separately. So how can you do that? Not all of them can be done like that, but sometimes you're lucky enough and you can, and when you can, then that's great, because it means basically you can just go ahead and solve using things that you already know how to do. So when they're separable, what it means is that you can put all of the x's on one side of the equation and all the y's on the other side of the equation, right? Or whatever your variables happen to be. So we'll have x and t in the actual equation, but the idea is that you need to be able to move them into two separate parts. So what I've done for you here is I've solved this separation of variables. I've taken this generic equation here, and I'm going to go ahead and take you through the steps of how to solve this thing. And this is very close to the actual one for the wave equation. Okay, so we start with a separable equation. Well, we won't know that it's separable until we try to separate it. We'll suppose that it's separable until we see that it is or that it isn't. And I'll show you how we can check. So the first thing we do is we start with this. It has two variables on each side. X and Y are the two variables, and it's second order. So the goal is we're trying to get to the second order linear homogeneous differential equation with just one variable in each equation so that we can solve this thing. Okay, so we're going to assume that it's going to be separable. And when we make the separability assumption, what we say is what's illustrated right here. Oh, now the pointer does not want to do anything. All right, hello, wake up, pointer. Okay, so you see that f of x and y could be separated into x of x and y of y. This is the separability assumption. This is a pretty broad assumption, and it's not really saying anything too specific about what the equation is. It's just saying that if you could break it into two different functions, that is the separability assumption. If it were not separable, it would mean that you weren't able to write x only in terms of x variables. If you had x and you had a cross term y, for example, then it wouldn't work. So if you could not separate x only in x and y, only in y, then it's not going to work. So this is what we're assuming that we're going to be able to do. So let's assume that it's going to be true, and we're going to substitute that in. So here is our function right here and here, and what we do is we substitute in. So this is the assumption that we made. We take that and we substitute it in to see what we would get. Okay, now what we notice is that there will be some constants we can factor. Now, if the function is split into two parts, one part is now going to be the x side and one will be the y side. So the idea is that you could factor some parts out. You might say, oh, but y of y is is the function, right? You cannot, it's not a, you can't factor that out. But if this will be the x side and this will be the y side, right? So what we're saying here is that we're assuming that all of the things on the left-hand side are only an x. So that means that the y of x, which we have right here, can be factored out because it's independent, right? This is only of x's. And also we see that y of y doesn't have any x's in it. So that means we can move it out. Same is going to be true on the other side, that the x's are going to be on the constants on this side. So this is the y side, so we're taking the derivative with respect to y, and that means x is being held constant. If you've done multivariable calculus, that's one of the techniques that we use in that. So this is the equation that we get at this point. Okay, next what we're going to do is we're going to divide and cancel to complete the separation of the variables, right? Because the problem is, all right, take a look at this one right here. The problem is that we've separated out the parts of the variable that it's depending on, right? So there's only x's here and there's only y here, and we said these are constants, but there still is a y on that side and there still is an x on this side. So even though they're like those constants, they're not gone. So what we could do is a transformation to remove them. So we're going to divide and cancel to complete the separation of the variables. So what we do is divide both sides by the separated function. So this will have the effect to cancel out the factor just extracted. So if you remember your days of algebra, as long as you divide the entire equation, both sides of the equation, by the same thing, then it's okay. So we're going to divide on this side by x of x and y of y, and the same over here, x of x, y of y. But the opposite terms will cancel. So on this left-hand side, which is supposed to be only for x's, the y of y's cancel out, and the right-hand side, which is only supposed to be for y's, the x part will cancel out. So now we're going to have a revised equation that has truly only x's on the left and only y's on the right. Now, let's take a look at this equation. Notice that something else has changed. I've gone from using the partials, that's these, the curly d's, right? These ones right here, the curly ones, to the normal d's. And that's because I have switched between being a partial differential equation to being an ordinary derivative. That is it really is truly only an x. So the change in notation from the partial derivatives down to here and having the separated variables is an important conceptual jump here, because on the left now we truly do only have x, which is represented now by the d's, and also the y's are all by themselves on the right-hand side as well. So we are making progress towards our goal of having only one variable on each side. Okay, now, if two things are equal, then that means that you could set them equal to a constant. So for example, if I said A equals 5 and B equals 5, then both A and B both equal 5, right? So if you had any two things that are equal to each other, you could set them equal to a constant. And we're going to do this because we want to actually break the equations apart. So here is what we're going to do. We're going to create some constant k. So the above equation can only be true if each half is equal to the same constant k. Otherwise, equality doesn't hold, right? The answer of whatever the left-hand side is has to be equal to the answer of whatever the right-hand side is. That's what the equal sign means. So that's why we're going to introduce the k. Now, when we introduce the k, which I've got right here, I set each side equal to the same k. Now, that's good progress. We now actually have two separate equations. This is good because I'm still thinking about that second order linear homogeneous differential equation that I want to use. So I like that it is separated out. Now, the next thing though is remember that in order to use that formulation, that it has to be homogeneous. Remember, a second order linear homogeneous differential equation, which means it's equal to 0. And right now, these things are not equal to 0, but we could change that so that it is. And in order to do that, what we need to do is move k to the other side of the equation. So now we have these two separate equations related by having a common k. And what I do is I just move the k over, and when I subtract k from both sides, I am left with 0 on either end, which now meets the criterion of it needing to be homogeneous. That's this one right here. So that's great. Now that is satisfied. Now, do you remember we also said that in order to use our formulation that the leading coefficient must be equal to 1. So we're kind of like moving into step 0. This step 5 and step 6 are kind of like step 0 of the next worksheet. They do overlap a little bit. That's the worksheet we did last time when we learned how to solve these. So what we need to do is we need to make the leading coefficient be equal to 1. Well, let's just take a look at the equation for a moment and see if we can understand where the leading coefficient is. Well, the derivative part is right here, and there is no first derivative part. And then k, there's also just minus k, right? So the coefficient of the leading term, so remember we also have to put them in rank order, d squared, this is the top term, right? The coefficient of that is 1 over x of x. We take a look at this one, and the leading coefficient is c over y of y. So what we need to do is we need to remove that leading coefficient to make it be 1. And how do you do that? Well, you just multiply everything out by the reciprocal of whatever that is so that they will cross cancel, right? That's the idea here, so that the leading coefficient will now be 1. So you do that to all the terms. So when you multiply k by x over x, right, that's how we get this. And then also we multiply the 0 by that term, but that just still stays equal to 0. And now we do the corresponding thing over on this side with the leading coefficient. So this one has x over 1. This one is going to be c and y of y. So you just take the reciprocal of that so that this cross cancels, c with c and y of y with y of y. Those cross cancel. And then we get out our revised equation down here. So we have the y of y being multiplied by k, and then the c in the denominator. And again, when we distribute to the 0, it just is 0. So in other words, you have to distribute to all terms in your algebraic expression. So now we have done that for both sides. Now, congratulations, we have now separated the variables. So let's just take a look at what we have accomplished. So we have converted a single partial differential equation. Remember, we had the equation up at the top. The single differential equation into two equivalent ordinary differential equations. So let's just review for 1 second and see what we had written about that up here, right? So here was our original equation, right? We had a partial differential equation in 2 variables. And when you have something in 2 variables, just like we said, that's the partial differential equation. Whereas what we want is the ordinary differential equation so that we can use our worksheet so that we can go ahead and solve that. Okay, so we successfully went from a PDE, partial differential equations, into 2 ODEs, one-dimensional, ordinary differential equations. Now, you might think conceptually like, well, how can you just have one equation and break it into 2 separate equations? Like, how does that work? Well, that was what the procedure we did was, but they're not truly independent. They are 2 equations. However, they share the same k. And this is very important. So we did separate them into 2 equations, which now each will be able to be solved. But whatever that k is, that k has to be the same k for both sides of the original equation because they are related when we did that breaking apart by setting them equal to a constant k. And that is where we have ended right here. So now, with that in mind, we can learn how to solve the wave equation. So let us move forward to that area. So I'm just going to zoom in a little bit. Let's give ourselves a little bit of space here. That's zoomed in a little too much. All right, great. So now what we want to do is solve the wave equation. Classical wave equation. All right, so let us just get in our minds what picture this is. Looks like this. Here's a wave. And this is our x-axis, okay? Right, this is the x-axis. We have x equals 0 here and x equals L, that's alpha length. And here we have the displacement, that's the displacement u of x and t. So this is, for example, a vibrating string. A vibrating string with fixed points. This is very important. These are fixed, right? It's their nodes, fixed points at x equals 0 and x equals L, the length of the string, and with an amplitude, the amplitude u of x and t is a function of both position, that's the x, and time. That's the t, right? And that's what this says up here. And this is precisely why this is a function of two variables. So now we are going to write the equation that describes this. The classical wave equation is given by d squared. Okay, this is my curly d. That's how that looks. U of x and t over d x squared equals 1 over v squared, that's velocity, d squared u of x and t over dt squared. Do you see how this looks very close to the equation we just solved? Okay, v equals velocity, which is speed and direction, right? It's a vector. Disturbance, moving along the string. And the boundary conditions, as we've mentioned, these are the bounds, right? Boundary condition. Do you remember we talked about boundary conditions last time and how to use those? Guess what's going to happen? And you okay, so just what this means is u of 0t equals 0 and u of lt equals 0. Just looking at the picture, what that means is that the displacement in the x-axis is always going to be 0, and that will be true anytime. It's not varying in time. That's what that means. And we have simply just written that in a little bit more of the mathematical ways. In other words, the ends of the string are always fixed, is what that actually means. Okay, so now what we need to do is do the separation of variables, which is almost identical to what we have just done together. And I do believe you have this in your homework. Separate the classical wave equation, which I will leave for you to do, right? So we start with this, d squared u of x and t over dx squared. This is nearly identical to the one we just did together, right? So instead of being a c, there's 1 over v squared, which is a constant, d squared, and the name of the variables is a little bit different. So I did it in the more generic form, right? And then you're going to, whoa, what just happened there? Then you're going to solve, see the worksheet. So you can work through that. And I will tell you what we get out in the end, which should look very much like what we solved in the worksheet, right? So that's going to look like this. D squared, notice that it's a regular D, D squared, x of x. Looks like there's third and come back. D of x over dx squared. Sorry, and stops working sometimes. That this does not mean anything. Over, oh, no, turn the eraser off. There we go. Over dx squared minus k x of x is a big X, just in case you can't tell. Big X equals 0. And we have d squared t of t. So we have this different letter. Again, d t squared. Oh, we need a little more space. Minus k times v squared t of t equals 0. Those are the answers that we should arrive at when we have done the separation of variables. Do you see that this over here is the x side? This is the position. So this is sometimes called the positional, and this is called temporal. Right, temporal L because it's time, right? And this is position x coordinates. Okay, when we have the separated equation, there's a few things we should take note of. Do you see that they're second order linear homogeneous differential equations? There's 2 of them here. We can solve each one using the procedure we learned last time. Note that k is not actually known, but it is what holds the equation together. See, they both have a k. The sign of k is going to be important. Do you remember that when we substitute in, there is the discriminant, right? The square root of something, right? The thing that's under that discriminant is going to determine whether it's going to be real roots or whether it's going to be imaginary roots. And that turns out to be very important. And k is the thing that goes under the square root side. So k is very important because it will determine what happens under the square root sign. I'm actually going to write that down for you. The sign of k is important because it will determine what happens under the square root sign. This will lead to whether it's real or imaginary roots. And as you remember, that determines the functional form, right? And that in turn determines functional form. So that will be very important. And since we don't know the sign of k, we have to try all the possibilities. All right, so the possibilities are what? K is less than 0, K equals 0, and K is greater than 0. Those are all the possibilities. So I will give you a spoiler alert. So the bottom line is that the K is less than 0 gives interesting results. You would have no way to know that. I've already solved them and they've already been solved. These two turn out to be trivial cases. And that is why we are going to take a look at K as less than 0 today, because that is the one that actually gives interesting results. How did I know it? Because I already solved them all. All right. Let us then go ahead and do it. All right, so solve it with K is less than 0. Let's do it. We already said that. Let K equal negative beta squared. Why? Because it will be convenient soon. Also, you would not know that before you solve this thing. But the reason why is because we're going to need to take the square root of something, and so having something squared is really helpful. Okay, now we need to pull down our equation. D squared x of x. So I'm picking my my positional side plus negative k x of x equals 0 from above. And now I'm going to sub in the definition of beta. D squared x of x over dx squared plus. Now, what I'm doing is I'm substituting in my negative beta, which flips the sign. Beta squared x of x equals 0. Sub in beta. And I'm going to try to be really good about putting a really long tail on my b's, on my betas, so that you can tell them apart from my b's, because there will be some b's coming up, and and they're not the same. So now we're ready to do the second order linear homogeneous differential equation procedure. Okay, so let's do the Newton form. This is y double prime plus, are there any y prime terms? No, 0 y prime plus beta squared. And now y is going to be our x of x equals 0. Okay, so this is Newton form. The other thing we did here is we said x of x equals our y, that y that we're looking for when we solved this thing last time. Now, match it up. What is p, right? We need to identify it here, so we should probably just put a little note over here. This is step 1. ID, p, and q, right? That's the goal. P equals 0, and q equals beta squared. Deduce P and Q by inspection. Great, we've identified P and Q. Step 2, what is step 2? It's the auxiliary equation. So let's do our auxiliary equation. M squared plus PM plus Q equals 0. This is the auxiliary equation, just given. And now the next thing we do is we sub into it m squared plus what's p? 0m plus q beta squared equals 0. Sub in p and q. Next thing we do is we're going to use the quadratic formula, right? So now we do m equals negative 0 plus or minus square root of 0 squared minus 4 times 1 times beta squared. Okay, all over 2a. But remember, a is always 1, the leading coefficient. Is quadratic formula. Okay, sub in. So now we're going to solve for m. What does m equal? So m equals, all right, simplifying. 0 plus or minus square root. 0 squared drops out. Negative 4 times 1 is 4, and beta squared, oh, got the close parentheses, 4 beta squared, all over 2 times, all over 2. So we can actually clean this up. We don't really need to write that. And the square root sign can be much smaller. Equals 0 plus or minus. What is the square root of 4? 2. What is the square root of beta squared? This is why we put the negative beta squared, because we can take the square root of it, so we can pull it out. So beta is the beta times beta is beta squared, and we also have negative 1 from the minus sign, so we have 0 plus or minus 2 beta I over 2. So now we can cross cancel. So really also we don't really need the 0 here either. So I'm just going to take that off to make it look a little neater. And then we can cross cancel the 2's. So this is equal to beta I plus or minus, right? That is our answer. And this is just doing simplify. Now, the next thing we need to do is we need to identify the real and imaginary components. So we write down the form m equals a plus or minus bi, and that is the general form for imaginaries. And now we have m equals, what was a? A is 0 plus or minus, what is b? Beta I. So a equals 0 and beta, b equals beta. Right, so sub in our solution and deduce A and B by inspection. Right, that means you just match them up. That's the A part, that's the B part. That's how you know what it is. All right, now we go to step 3. That's select your form and sub in. All right, that's what we're doing here. Okay, so what do we have? We have complex roots case. And from that, we then use our worksheet to select the correct form. And the correct form is this one, y of x equals e to the ax times c1 cosine bx plus c2 sine bx. And this is just select the form. Okay, now we're going to substitute in a and b. So a equals 0 and b equals beta. Y of x equals e to the a, what's x? Oh no, I did it wrong. E to the a is the thing we need to sub in. A is 0, so this one, 0x, like that. Now, C1 is still not known. Cosine, what is B? It's beta, so we substitute in beta, x plus C2. Sine B, we're also supposed to substitute in, that's beta, x. This is sub in. And now we could do some simplification. So taking a look at this, anything to the 0 power is 1, including e to that power. So that just becomes a 1 times that thing. So that simplifies things quite a bit. So that means now we can have y of x equals C1 cosine beta x plus C2 sine beta x. And that's just simplified. So now we have arrived at this. So remember that we had substituted the name here, so we switched over the x for just the y to make it consistent with our worksheet. So our solution then is that the function x of x is equal to the y of x, right? Because we just switched the name. And now we could use a more generic names. So I'm just going to change the name of my constant to a cosine beta x plus b sine beta x, where a is, so the triple equal sign means defined, and b is defined as C2. This just is to match reading. There, that's generally how textbooks call them. Math books tend to call them C1, C2. Physical chemistry tends to call them A and B. So I've just changed them out, but it means the same thing. This is the general solution. How do you recognize it as the general solution? Well, we recognize that it is the general solution because we still have the C's, I mean the A's and the B's, what used to be the C's a moment ago. They are not solved for. And so this is how we recognize it as the general form. Very important equation right there. Okay, great. Now, what happens next? Do you remember that we have the boundary conditions? So what we need to do now is we need to apply the boundary conditions. Oops. Yes. All right. Apply the boundary conditions is the next thing we need to do. So let us consider what the boundary conditions are. Those were the bounds that we had for the strings, and the bounds were the two ends of the strings are, well, bound. So let's write that up in a mathematical way. So we could write x of 0 equals 0. That's the left-hand bound. And x of L equals 0. These are given boundaries for the string, as given as part of the problem. We also need our general solution. X of x equals a cosine beta x plus b. Okay, yeah. So this is where we have a's and like b's and betas mixed. B, these are not the same. This is b and that's beta. B x equals 0. Let's just make sure. Yeah, that's B and beta. Okay, just to be sure that you have that not mixed. This is the solution from above. Solution from above. And now what we're going to do is we are going to sub in the boundary condition. The boundary condition of x of 0 equals 0. Okay, so now we're going to do a cosine beta wherever you see an x, right? So this is like f of x. Now we're doing f of 0. Wherever you see the x, you substitute in the 0 plus b sine beta, wherever you see x, substitute in a 0 equals 0. Well, how do you know it's equal to 0? Well, it's because that's part of the bound. X of 0 equals 0. It means there's no displacement at the end. All right, now, do you remember there are a few things we need to remember. So let's take a look at this. We have beta times 0. This is just 0, and beta times 0, that also is just 0, which makes this a cosine. Well, here we can just write it out. Equals a cosine of 0, or here I'm just gonna even skip the parentheses because we're not really substituting anything in. A cosine of 0 plus b, oops, sine, sorry, wrong one, sine. Too fast. Sine 0 equals 0. Now, do you remember about your sine and cosines? What is the sine of 0? Recall. Cosine of 0 equals 1, and sine of 0 equals 0. Right? So we can remember those facts. So by remembering those facts, we can now make this be even more simplified. So cosine of 0, and cosine of 0 is 1, and sine of 0 is 0. So in other words, what we have is a times 1 plus b times 0 equals 0. So b times 0 just drops out. So x of 0, this is just carrying down here, equals a equals 0. We have our first answer, right? A equals 0. That is the information that we have. Okay, and these are all just simplified. Okay, first bound solution. Yay. Okay, great. Now we have two boundaries though. So remember, let's just take a look back up here. The other boundary was x of L equals 0. So now we're going to need to go ahead and solve that one. So now we solve for the second bound. Solve for second bound. And let's do it. X of x equals a cosine bx plus sorry, that one's beta, b sine beta x equals 0. This is the solution from above. But we know some information. Now we're going to substitute in x of L, right? Because we're doing for the second bound, equals a cosine beta, wherever you see an x, substitute in an L. That's a beta. Should I make that? Let me make that more clear for you, just to be sure. That's a beta L plus, this is a B, sine, here's the beta again. Beta, and wherever you see an x, put an L, equals 0. Sub in the second bound. Okay. But we also know that a equals 0. So now we're going to sub in a equals 0. So x of L equals 0 times cosine beta of L plus, and that's the only change, b sine beta of L equals 0. Okay, now that means that this whole term is multiplied out by 0, which means that is gone. So in other words, we have x of L equals b sine beta L equals 0. This is simplified. Okay. So, do you remember your multiplicative properties of 0? How do you multiply two things together and get the answer to be 0? So we have two terms. We have, and I'll just make that explicit by putting a little multiplication dot there. Okay, so how can you get the answer to be 0? Well, I mean, it could be 0 times 0. Everything could be 0. That would be very uninteresting. You could have B be 0. So if B were 0, that means that, well, what's B? It's the integration constant. So you could have the B times some number. If B were 0, that would give 0. Or the other thing you could have is the sign of BL would be equal to 0. So if the integration constant is 0, that's not a very interesting answer because there could be any integration constant, right? So you change it so the integration constant is not 0. So the sign beta L equals 0 is very interesting. And of course, it's the sine wave, right? So when is the sign gonna be 0? Well, the sign will be 0. Remember, it's repeating pi, 2 pi, 3 pi, 0. 0 also is that. That just means everything's 0. Yeah. So there are multiple solutions to this thing because of the sign. So now let us just write down a few facts here to capture those ideas we have just been exploring. So either B equals 0, that's the integration constant. This is not interesting. That is because it's the integration constant. Or sine EL equals 0. This is interesting. Okay, now we were mentioning about those multiple solutions. They called it sine of something, call it theta equals 0, because sine something has to be equal to 0 for theta equals 0, pi, 2 pi. Are you seeing a pattern here? Right, and so on. So then BL, right? So BL, the theta, the thing, equals n pi for n equals 1, 2, 3, and so on. We'll omit 0. Which implies the boundary, it's the same bound condition, right? So the interesting things happen when n is an integral number. And we will also write beta equals n pi over L, which we will need later. Just hold that thought. This was just rearranged. Okay. Next, x of L equals B sine BL equals 0. This is from above. X of x equals B sine BX of beta x equals 0. This is just switch back. I'm just switching the name of the coordinate, okay? Because I will want to show you something. Okay, x of x equals B sine nx n pi x equals 0. Sub in BL equals n pi for n equals 1, 2, 3, blah, blah, blah. Okay. Now they're going to divide L by L. X of X, because we want it to be per unit L. E n X L equals 0. The reason for doing this is divide by L to make the answer per unit L, which is the length of the string. So we are almost done. We could do one more fancy math step to make this match textbooks. B sine n pi x over L, that's from the step above, for n in n, what is that? That may not be. You may or may not recognize these symbols. What this just means is it means the n equals, this stuff right here means the same thing as this stands for natural counting numbers. This here means in. So this is just fancy math stuff for that. But this then gives us our solved positional part of the equation. So this warrants a highlight, but we have some things here in blue. So I'm going to pick this color. You won't mind if I use purple, right? Oops, blue for the other one. We'll put this, oops. Guy hit the scroll bar there. All right. There we go. So let's just take a quick look at what we did here. We did our worksheet, which did the separation of variables. After we separated out the variables, we took a look at the actual wave equation, which has the same separation procedure as outlined above. And I told you the answers to those. So you'll push those. The only thing that's really different is the C. Has a 1 over v squared. So wherever you see 1 over v squared, you're right. It's the same as C for the one we did together. Okay. Now we have our separated wave equations into the positional and the temporal part, X and T. We talked about the sign of K, right? So K has to be negative, 0, or positive, and I purposely selected K is less than 0 because it's going to give us some interesting answers. We took K and we went ahead and solved this with second order linear homogeneous differential equations, which we did here to get our solution. And then we applied the boundary conditions. So what do you suppose is next? Well, the next thing we should do is we should solve the temporal part of the equation, right? Do you see that there's actually 6 things you could do here, right? You could solve for K is less than 0 in the position and K is less than 0 in the temporal. And then you can do K is equal to 0, position and temporal, and K is greater than 0 and positional and temporal. So that's 6 different combinations. And then for each of those combinations, you have 2 bounds. So there are 12 possible boundary conditions you can solve for, any of which could give interesting answers in principle. But the truth of the matter is they do not all yield interesting answers. How do I know? Because I solved them. You would not know unless you solved them. All right, so what we're going to do is solve the temporal equation. So let us now solve the temporal equation. Yeah, this is for k is less than 0. Okay, so we go back to our separated part. Again, we have the ordinary differential equation, right? So we have the d's, normal d's, dt squared minus k v squared t of t equals 0. This is from above when we finish separating the equations. V squared t of t over dt squared plus. So we're gonna do the same thing that we did before. T of t equals 0. So let k equal negative beta squared. This is just like we did before, or future convenience. It's because you're gonna put it under the discriminant when we go to solving the quadratic equation, right? And it'll be a pain in the neck to have a square root of something you can't pull out. But if you make it beta squared, you can pull it out. Okay, now we're gonna do step 1, deduce P and Q. Okay, so that's what we're doing here. So the first thing we're gonna do is write it in the Newton form. Y double prime is this term right here. Do you see any y prime terms? I don't see any. 0 y prime plus beta squared v squared. And now our y is gonna be t of t equals 0. So Newton's notation. And also we'll let y be t of t just to make it more consistent with our worksheet. Now we can take a look, and by inspection, P equals 0, right? This is the one that goes with P, and Q equals beta squared V squared. ID P and Q by inspection. All right. Now, step 2, auxiliary equation. All right. M squared plus PM plus Q equals 0. This is the auxiliary. And now sub in M squared plus what's P, 0M plus what's Q, beta squared V squared equals 0. This is sub in P and Q, just like we've done before. And now we're going to use the quadratic equation. M equals negative 0 plus or minus square root V squared, which is 0 squared, which is P, minus 4 times A, which is always 1 in these equations, and Q, which is beta squared V squared, all over 2 times 1. This is the quadratic equation. Right, next we're going to work on simplifying this. Equals plus or minus, right? 0 drops out. Square root of 0 squared minus 4 beta squared V squared all over 2. Oh, now we can make this a little smaller. We got a little carried away there with that. Close that off. Okay. Now we can pull this out of the things in the radical. All right, what is the square root of beta squared? It's beta. What is the square root of V squared? It's V. We also have a minus sign under there. What's the square root of minus 1? It's I. So we have BVI over 2. Oh, wait, I forgot the 4. Sorry, there's also a 4 here. It's from this right here. I just forgot to write it. Sorry, there should be a 2 up here. And now the 2's will cancel. Great. Equals plus or minus BVI. And this was all simplify. Okay, Now, the next thing we do is m equals a plus or minus bi. This is the general form, complex numbers. And then we write in our form, m equals what's a? There's nothing. It's 0 plus or minus what's beta? It's bv times I. This is our solution. And now we're going to deduce a and b by looking at it. A equals 0. That's this part right here. And b, whoa, that was a little wild. B equals beta v. This is deduce A and B by inspection. Okay, next. Step 3. Substitute the correct to the correct form. Right? Oops. Oops. Oh, move this. Oh, is this? Can I move this? Ooh, ooh, yes. Good. Okay, stop. Okay, step 3. Substitute the correct form. This is complex roots. Y of x equals e to the ax times c1 cosine bx plus c2 sine bx. This is the general form. And now, well, I need to watch my time. Okay, now we're going to sub in the actual answer. Y of the x equals e. Anytime we see a, we substitute in a, which is 0. X times c1 cosine, what is b? bv. So we substitute in the beta v. X plus c2 sine, what is b? It's beta v. X, this is sub in a and b. Now, let's see if we could simplify anything here. Oh, yes, I do see anything to the 0 power is 1. Is this starting to look a little familiar? Just gonna move this over for convenience and C1 cosine beta Vx plus C2 sine beta Vx. This is simplify. And just to be exact, I suppose these probably should be in parentheses like that. Okay. Now, we've solved this using our worksheet, which used x, but instead of x, let's use t because this is the temporal equation. So y of t equals c1 cosine beta vt plus c2 sine beta vt. All right, x equals t for the temporal equation. All right, great. We have multiple constants. So do you agree that if you have two constants multiplied together, it's just going to be a constant? So I mean, if you just have like 2 times 3, it's just going to be 6, right? There, you could represent it as 2 times 3, but why make it complicated? You could just combine them. So let's combine. Okay, so I'm going to define omega sub n. So again, triple equal signs means I'm defining it to be that beta sub beta v. And remember that we had the beta definition from above. This was from the definition above. This one is the definition, and then this was the position from above when we solved the other equation. So now we have T of T equals C1 cosine BVT plus C2 sine BVT. And now the BVs are gonna get substituted. So I'm just gonna do like this so you can see how I'm doing it. So now we have T of T equals, now also what I'm gonna do is I'm gonna change these ones to a different name, a constant by a different name. It's like a rose by any name. Would it smell the same? Good. Emily Dickinson. A rose by any other name would smell just as nice, right? So change your constant's name. D cosine omega sub n t plus E sine omega sub n t. What would normally happen at this point? At this point, we would normally solve for the boundary conditions. However, did you notice that we did not have any boundary conditions available? Why not? Because it is the temporal equation and it is the same for all t. So there are no boundary conditions. So this is another important waypoint in our discussion today. So I'm going to box that. That's worth boxing. We would now normally sub in the bounds. However, to solve for the constants, D and E, right? That's the ones that are here. However, none for time are given. It's because it's for all t. Right, that was also given. So we're done with this one for the moment. So you might think that we're completely done, but not quite. Because what we need to do is now we need to write the equation for u of x and t. Now we need to why does this keeps deleting? Hello, Ben, come back. Now we need to write the equation for x and t for both positional and temporal solutions all together. Let's see, pen is back. Yeah. Right, so we need to go back for both variables, for both positional and temporal. Sorry, the pen is going a little crazy. U of x and t equals x of x, t of t. Do you remember this? So we have now solved each of those halves. So what we need to do is we need to put them back in. Equals b sine n pi x over L That's the left-hand side. And we have d cosine omega sub nt plus e sine omega sub nt, or n equals 1, 2, 3, blah, blah. Oops, sorry. Back. Okay. That happens when I hit the margin on the side. Okay, equals. Now what I'm going to do is I'm going to do a rearranging. So this one right here, I want to write it a different way. Sine n pi x over L times, oh, no, not beta. No, 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 no. B, regular B. B, B. So I'm just going to do like that, right? And just change the order. B times D cosine omega sub nt plus E sine omega sub nt, or n equals 1, 2, 3. Okay, now what I can do is I can distribute. Okay, so this was, I'm running out of space to write. Let me zoom in a little more. Stop. No, I don't want to type. Okay, this was sub in. That's sub the solutions. This one is rearrange. Okay, now what I'm going to do, actually what I'm going to do is I'm going to move a little more to the left. A little drift here. All right, now I'm going to distribute sine n pi x over L. Now the B is going to distribute over this parentheses, open parentheses. B D cosine omega sub nt plus B E sine omega sub nt, or n. I'm not going to keep writing this every time, right? It's the same thing. And this is distribute. Okay, and now the next thing we can do is we have again this situation of constants. Okay, so you see is now we have multiple constants all together, and this is an E, just to be clear. Okay, now what we can do is we can name yet another constant so that we can put those together. So, oh, I need my U of X and T again. U of X and 10. We are almost done. Don't die on me now. Why are you doing this? U of X and T equals sine n pi x over L. And now we'll define a new constant, F cosine omega sub nt plus G sine omega sub nt. So what we've done is we have defined F is defined to be BD, and G is defined to be BE. This is combined constants. That's what's happening there. So there we have it. Now this is a solution to the differential equation, but since each omega sub x and t is a solution, their sum is also a solution. Could you check? This is the solution to the differential equation. But since each u sub n of x and t is a solution. So too, their sum is also a solution. So we can write the sum like so. U of x and t equals the sum of n equals 1 to infinity. And this just changes up the order, but f cosine omega sub n t plus g sine omega sub n t times sine n pi x over L. Oh, oops. I have an extra parentheses here. That's not right. That's better. 4 n equals 1, 2, 3. Oh, okay. Now, consider that sine and cosine are actually the same function. Do you agree that sine and cosine are basically the same shape of a function and that there is an offset? If you could pick up the function and translate just the plain sine function and cosine function, usually you think about maybe translating cosine to sine, right? Because sine starts at 0, 0. You could just pick it up and slide it over, and they would be the same thing. Now consider that sine and cosine are actually the same function with an offset translation. If you did that in your pre-calculus. We did that in pre-calc when I taught it about translating the functions. So long as they're taking the sine and cosine of the same thing, they can be translated to superimpose them. Doesn't work if you have like sine of 3 and cosine of 2, but if you have sine of 2 and cosine of 2, then this will work. This translation is achieved by adding a translation constant. Which is called this one. That's B, I think. And for sine and cosine functions is referred to as the phase angle. This one right here. Thus, we have u of x and t equals, and we have the summation from the last step, n equals 1 to infinity, a sub n cosine omega nt plus, as the translation, omega sub n sine n pi x over L, or n equals 1, 2, 3, blah, blah, blah. equals n equals 1 to infinity u sub n x and t. Ooh, so we solved the thing that we set out to do. All right, and I am a few minutes over, but not horribly so. Okay. There you go. It's very important. Give it a star. Very important equation. What does this mean? Interpretation of the classical wave equation. Ah, you can't die now. All right, when the string is plucked, its shape or the displacement will evolve according to view x and t, the displacement equation. The displacement will evolve according to view of x and t, the displacement equation. Okay, that's what this tells us. Each u sub n of x and t is called a normal mode. Time dependence of each normal mode represents harmonic motion frequency. This is new. U sub n equals omega sub n over 2 pi equals v sub n over 2L. This is velocity. Notice the two v's. So therefore, omega sub n equals vv equals n pi r n pi v over L. N equals 1, 2, 3. So this gives the quantization numbers. Quantization numbers, that is the n's, give rise to the different waves. These are the overtones. This is how you get overtones in stringed instruments. I'm going to draw pictures. This is the same string, same width. Yes, okay. N equals 1, n equals 2, n equals 3. should be equal thirds. There's a node. Number of nodes equals 2, and so on. Standing waves then are going to result from binding the ends of the string. And this, my friends, is precisely what gives you the quantization in a classical equation. And do you remember we talked about quantization and we wondered where that came from? In quantum mechanics, binding the ends gives you that. Standing waves results from binding the ends of the string. And so when we talk about the quantization, remember we had the picture like this about waves that needed to go around it and that they wouldn't interfere. So you'd put your next wave on there and it would continue and go like this to match the same one. This is exactly what we're talking about. This is not a classical picture. This is a picture for quantum mechanics, but it is going to be the same mathematics. It is taking effect that is causing that to happen. All right, I am going to stop sharing now. Thank you all so much for joining us. I hope that you enjoyed learning about quantum mechanics. We hope that the worksheet helped you understand separation of variables. And we went ahead and solved a couple of those things. Remember, we only solved for the situation where k is less than 0. There's also the cases of k it's greater than 0 or k equals 0, which gives us not important answers. These answers that we saw today are the ones that are interesting, and we saw that because they actually cause these waves to appear when we solve the equation. And that is how we get standing waves in classical sense. So some of the things we will want to know next time around. Well, actually, next time we're just going to talk about the Schrödinger equation. But when we start talking about quantum systems, we'll want to understand how those waves happen in those systems, which is going to arrive in a very similar way, but from solving the Schrödinger equation, which will have equations that explains quantum mechanical systems instead of classical systems. So hope you found this helpful. Thanks so much for joining us, and we will talk to you next time. See you later. Yes.